So how's everyone doing this afternoon? Okay, all caffeinated up and sugared up, hopefully? Okay. So what we're going to talk about today is something that might be a little old for some of us. How many of you have, in the past, not currently, used C++ as a language? Oh, good, great. How many of you currently use C++ as a language? Okay, that's usually what, is the experience. It is kind of older, but like everything, it's been around a long time. And languages are really tools. So if you're not currently using C++ and you haven't in the past, but you might be wondering, why would you want to learn it? Languages are tools. So learning a language, new languages, is actually a good way of, sort of expanding your toolbox. So I hope through this to sort of give you an idea of not just, here's the language, but here's kind of what the language has evolved into recently. Here's applying it to some non-trivial kinds of projects that are still ongoing. And here's some of the rough edges. Here's some of the good things. Here's some of the bad things about it. And no talk on C++ is complete without at least one, and hopefully more, Bjorn Stroustrup quotes. Here's one. The only two kinds of languages, the ones people complain about and the ones nobody uses. That's pretty much true. If you think about any language, can you name anyone who uses it, and can you name anyone who has complained about it recently in the last 24 hours? So think about that. Nothing's quite perfect. Oh, and we're going to see that C++ is by no means perfect. So within the last couple years, there's been two projects that I've been fortunate enough to be involved with that have had C++ aspects to them. The first is Aeron, and the second is Reactive Socket. And they have both used modern C++ techniques. They've used C++ 11, which is 2011 standard, and C++ 14, 2014 standard. So these are new features of the languages. And we want to talk about what these are, sort of give you an idea of where they fit, what constitutes those aspects of the language, and sort of what lessons we've learned and how things have turned out and how they're going. So the first thing is Aeron and C++. So Aeron is a truly modern messaging transport. My background is I am a network protocol designer by trade. I've done and designed many different messaging transports and protocols going back all the way back to the very early 90s. And so what Aeron tries to do is try to break the cycle of most messaging systems being feature bloated and complicated, and try to trim it down to just a transport, that is faster than what is out there. Most of that right now are not fast enough, especially for trading systems. And what you want is low and predictable latency, but at high throughput. So it is absolutely key that it's predictable. And we're in a new world. Most of the messaging systems were designed in the later 90s, if you're lucky. Some were even designed in the later 80s. And sort of things like multi-core, multi-socket, and cloud, these are foreign to most of these the architectures. You're also looking at a lot of different media that has changed over the years. The idea of using IPC or shared memory as a media is somewhat new as well. So Aeron is trying a new approach. Here's the team. Martin Thompson, who talked earlier, Richard Warburton, and myself. We're not the best looking group, but hopefully we're not too dumb. So what messaging tries to do is to connect publishers to subscribers. And Aeron uses the terms channel and within a channel different streams as sort of an abstraction to connect them to one another. And they happen at various numbers of subscribers, numbers of publishers as well. And it's a library, not a framework. So in other words, most messaging systems, if you think of something like, how many of you are afflicted with a disease I call JMS? Okay, that is a framework. That's this heavyweight thing that you fit yourself into. That's not really what most people want to do. It's just how things like Java messaging system has sort of evolved. You want to be able to have a composable design where different pieces can be fitted in, fit for purpose. And if you're thinking about a messaging transport or any type of protocol, it's got to fit somewhere. So this fits in the OSI layer 4 transport for message-oriented streams, which means it has a certain set of criteria. It's connection-oriented. It does provide reliability, best effort reliability. There is built-in flow control, which is one thing that is different than other protocols in this area. There is a place for congestion avoidance and control and allows multiplexing. The architecture is important. It especially is important to understanding sort of some of the C++ challenges that are involved with Aeron. So, for example, a publisher is appending to a replicated log that is being read by a subscriber. And this can happen in both directions. And there is some sort of sender which is replicating it onto a receiver. And the pieces on the sides there are the actual logs themselves. We have a special structure that is a shared memory structure called a log buffer that has certain characteristics about it. And there are different pieces, conductors for doing different administration things and how applications fit into this. There is something called a media driver that sort of allows us to sort of separate the senders and receivers as well, and to sort of give them a nice place of sort of separation. You'll notice in the design, if you ever look at Aeron on GitHub, you'll see these actual terms: conductor, sender, receiver. We believe in actually looking at the architecture and reflecting it in the code as directly as possible. And so sort of where does C++ fit into this? Well, one way to think about this is that those edges where the client lives are the application APIs. So these where all the different languages kind of come together: Java, C, C++, C#. We have Go as well, and they all fit within that. But they have some significant challenges, and we'll get into that. But you can sort of look at the fact that there are shared memory data structures which are actually being shared between these languages. The media driver is one, but there actually is other languages as well. So the media driver, currently, we designed it in Java initially, but I say currently, let's hold on to that. So that's one project. Aeron is a low and predictable latency, high throughput messaging transport, primarily designed with financial services in mind. It was sponsored by a very large US exchange for Martin Thompson and I and Richard Warburton to produce and to put out under an Apache license. It has a C++ side to it. It also has other language aspects to it. Another project that I'm involved with is something called Reactive Socket. Now, Reactive Socket is a protocol, but let's think about the application for a moment. Today, asynchronous is the norm. If you think of Node, it's asynchronous. You think of a lot of other frameworks that are out there. Most of them are asynchronous. If you think of messaging, going back years and years and years, it's all asynchronous. So it actually is today that the idea of asynchrony is the norm. When you have synchronous kind of calls and blocking, you are restricted to the round trip time of your media, whether that be memory or network or whatever media you're going over top of communicating with. So asynchrony is a mechanism, and you've heard it today with a couple other talks, of breaking that, where you can now do two separations. You can do latency and throughput can now be separated. And you can do things at a certain latency, which doesn't grow as fast as throughput, if we look at how technology's gone. But it's complicated. So if you look at things like Node, it is very complicated to do things like retries and errors and exceptions and everything else within that flow. Some would look at it as, callback hell. And it's the need for simplicity, but the tools aren't there. And so what you get is this lure of complexity. You get this lure of, I have to do this operation, but I have to do it outside of the thread that it would be initiated on. And so you get very complicated structures that kind of start to, how do I handle a lot of different cases? And we also think that, it's really thought of as asynchronous kind of platforms are hard to do. Well, actually, all that happens in that is that they're bringing forward all the problems that you would normally have with asynchronous communication, but you never solve with the asynchronous communication. You usually just punt and say, I don't know how to handle that error. So it's this lure of complexity, but it's the need for simplicity that has arisen. Well, what happens is composition of these things is very difficult. So it's easy when you just have a, one message coming in, but now if you have a message coming in followed by a potential error condition, followed by another message that can come in that has a dependency on that, that's how thing in composition gets to be very difficult. We do have a couple different ideas about how to make that easier. Reactive extensions is something which has come about to combat that composition problem and to get rid of callback hell. Now, some consider that it's actually trading one kind of hell for another. That might be true. But what it does do is it does simplify some of the more common patterns into things which can be more composable and can be reused across different applications. There are many different languages for reactive extensions. Started out in C Sharp, but it has sort of evolved around into Java. It's used throughout, and there are C++ sides to this as well. And it all fits around the idea of the observable pattern. So an observable, and then you have a subscription on it, and then you have events that come in. There are challenges, though. Reactive extensions is really sort of in the area where back pressure is not something which is taken care of in the normal model for reactive extensions. It's just assumed to be blocking. So every time an event comes in, it's blocking another event behind it. That cannot be, that is somewhat limiting in terms of scaling up. So the idea of how to do this from an asynchronous perspective and push back pressure through systems, in a non-blocking way has to be handled. The other thing is that when you have something like reactive extensions, how do you actually handle the situation of heterogeneous connectivity between different languages? Well, that first problem, dealing with back pressure, is really where reactive streams has come on. And reactive streams is part of our XJava 2.0. It's been done in akka streams. It's actually in GEP 266 for Java under Java Util Concurrent Flow. It's an interface. And it adds the concept of requesting more data and being able to cancel and other asynchronous things which are done within a flow. So it has actually quite a bit to sort of address that. Now, it's not perfect. In fact, I would change some things about reactive stream if I could. But it is better than the alternative of only having blocking back pressure. But it doesn't solve everything. Because what it does do is it introduces asynchronous concepts to something which is basically blocking by nature and is sort of limited into one address space. When you break it apart and now you have the ability to essentially have an asynchronous communication, you can actually then format that on a wire. You can send it between two different systems. One system can be in Java, another system could be in C++. This is heterogeneous connectivity. So that means that you have to have something which handles it, and that's what reactive sockets is a protocol to actually allow these systems to talk to one another. The Reactive Systems API is what is assumed there, but there are different implementations. There's Java, there's JavaScript, there's C++, which is one thing I'll talk about. There's Go. And these systems are in production. Java is used at Netflix. Reactive Socket is used on the edge part of the Netflix API. Go is used at a few other places. C++, this project is going to be used by a very large user of this technology. So these are systems which are already being used and using things like Reactive Socket. Here's a question. If you have a protocol like this, but it's only limited to one language, what would you call that? Can you think of any protocols that do that? Java serialization is one, right? It doesn't have to really interoperate. It could, it does, but it doesn't really need it under most cases, right? Think about that. Is there a reason, if you just have one language, for you to actually go through the trouble of standardizing a protocol? Think about that. Keep it in the back of your mind for a little bit. We'll come back to it. So those are the two projects. And they have a little bit of relation to one another. There's protocols involved. There's a few other things involved. And they all both have C++ attached to them. So what really constitutes modern C++? Because that's what's in the title. So if we look, Scott Myers has sort of coined this term for a long time. And it's kind of been a moving target, okay? It used to be that modern C++ was C++ 98. That was modern. And then it was C++ 03, and then it was, C++ 11, and it's C++ 14, and there's also C++ 17. So it's kind of a moving target. Whatever is, the latest C++ is really what we consider to be modern. But for purposes of what we're going to talk about, we're going to sort of start with C++ 11 and move, forward. And think of it this way. Another quote from Bjorn Stroustrup is, within C++ is a much simpler and cleaner language struggling to get out. I'd like to think that there is also within Java a much simpler and much more performant language that is trying to get out. I'd like to think that within Go there's a much better language trying to get out. We can think of this for every language. This is what we want. We want, actually, the language designers to be struggling with making things simpler, with making them cleaner. And C++ 11 actually does do this. So what is the main concept? Let's just take C++ 11 and go forward. What makes it different than a lot of the other languages before it? I would say, and this is me, but there are others who agree, that the core thing here is resource ownership and lifetime. Now, when you're thinking about a systems language, a native language, one thing you're thinking about a lot of times is managing resources, whether that be file handles, or if you're thinking gaming, you're also thinking about textures and all kinds of other things which are resources. You may be thinking also about memory, and that's true. Most languages that are garbage collected, they sort of think of memory as something you don't need to worry about until you actually realize that you actually do, because you have to release what you're using at least enough so that a cycle can be detected that isn't referenced by anything outside of it. Well, hold on to that for a minute. So resource ownership and lifetime is one thing that C++ 11 attempts to put in the forefront. And what happens when the idea of a resource ownership and the lifetime of it is sort of given into a feature of the language, then the ideas of scope, decoupling, and dependency start to come into play. What is the scope of an object or a resource? What coupling is related to that? What other resources and dependencies that come along? Modern C++ has idioms. There are a few. The most prevalent is resource acquisition as initialization, RAII. And now it permeates the whole language and the standard library. Lock guard is an example. You take the lock when you enter the scope. You release it when you go out of scope. Unique pointer and shared pointer, which are part of that resource ownership and lifetime, they work the same way. When they're created, you create the object. When all the references to it go away, it goes away. That is a core concept, which has been in C++ for quite some time. It's now been more codified into the language through the standard library. But by no means is it the only idiom. PIMPL, or private implementation, or pointer implementation, curiously recurring template pattern, erase remove idiom, substitution failure is not an error. If you're familiar with metaprogramming, that's one that's kind of a fairly important one. And there's a few more. So every language has idioms, whether we use them or not. Java has a whole set of idioms. Erlang has a lot of idioms, for example. So, but to the level of how an idiom has influenced the language, I don't think that something like RAII can really be compared, except there are certain things within Erlang that are very close to it. With that idea of those idioms, the idea of smart pointers, has come along. These are, there are three different types of smart pointers. The first is shared pointer, which means shared ownership. Unique pointer, which means unique ownership. And weak pointer, meaning no ownership, but a reference. This is all you have. So everything has to fit into that, into those three things. And if you're thinking about it and you know other languages, you may be thinking of things like, lambdas and function objects as well is another feature of modern C++ that was added. And this was added actually before Java had lambdas. Function objects have been around for quite some time. Atomics are another part of C++11, a very important part because it introduced a memory model to C++. And these were added as a set of templates which are around a different set of types and some other things that were added. We'll come back to these for a moment because they'll be very important to us. Thread support, so actually having standardized across different platforms, threads, mutex, asynchronous calls for task-based parallelization, promises and futures, these were added. The big money feature of C++11 though was something called move construction and assignment. When you actually have to take one object, pass it around, the idea of passing ownership or passing reference or copying, those different types of things kind of bubbled up to the surface. This was the performance win, or at least it was thought to be the performance win. Turned out that it is important, but there are some caveats. When you think about moving, the idea of moving an object versus copying it, moving may not be the right term. If you're thinking about ownership, giving and taking ownership make much more sense, right? But the concept of moving is really what is being done physically. You're moving it from one container to another. And it really has to do with ownership. And how these things interact with copying has actually been codified very, very well in something called the rule of 3 originally. It's now called the rule of 5, and then there's also the rule of 0. And they really talk about more like ownership and how these things interact with one another. They're very well codified. And the tool chain for C and C++ has changed over the years. We actually have quite a few nice tools like CMake, which is used for very large projects and a lot of small ones. We have a whole set of Google pieces that are very good, Google Test, Google Mock, Google Benchmark. There's also things like that have been around for a while, like Boost. Facebook has Folly, which is a set of Boost Plus, a lot of other features, and a lot of actually pretty good pieces. Quite a plethora of different things which are used within the tool chain and are fairly useful. So that kind of gives the idea of mostly, sort of here's the set of, the modern C++ pieces. Let's now think about what kind of lessons were learned from both things like Reactive Socket and Aeron. Now I'll say up front that there's only one thing which is any specific to one actual project. When we get to atomics, that was specific to Aeron. All the other things are things that have been encountered by both projects. And I'll sort of point out, why some of these are a little bit harder. So given this list, what things do you think stand out the most to you if you're thinking about, a project that you would just start from scratch and then you wanted to use some of these features? What do you think would be the most problematic? Whenever you have new kind of paradigms or new ways of interaction, that's always something that is going to stand out as a red flag. So something like some of the idioms, smart pointers might be there. Stack allocation has been around a long time, so there shouldn't be anything there. Lambdas and function objects, probably a lot of things around that because those are all syntactically different, have different kinds of trade-offs, especially something that's supposed to be fairly performance sensitive. Atomics probably has something. Thread support, oh yeah, anytime you add a new standardized API, you're probably going to have it. Move construction and assignment, maybe. Tool chain, probably not. Your tool chain, you're dealing with new tools or tools that have evolved, so they may or may not be issues. I'll tell you that mostly tool chains are not issues. They're kind of known quantities. Once you use them, you adapt. How many of you use Maven on a regular basis? Anyone like Maven? What's the first rule of Maven? You don't understand Maven. That's how you deal with Maven. You deal with Maven by first realizing that you'll never understand it and you'll never agree with it. Once you realize that, you can just be blissfully ignorant and do whatever you need to do. Because always you realize that you're never going to know what it's going to do and you're never going to agree with it. You just have to understand what it's trying to do. That's most tool chains. So let's take some of these lessons. We're going to specifically look at RAII and smart pointers. My best advice for dealing with this is basically give in to smart pointers. Don't try to fight it. You have 3 different types. Fit everything into it. Try to avoid using any raw pointers. You'll find that, the dark side ain't so bad. But it does, because it does a couple different things that I don't think were intentional, but are good. Okay, well, let's go back for a moment. We talked about there being 3 different things: shared ownership, unique ownership, and reference. How do we deal with cycles? How many of you have dealt with cycles in other C++ or C applications before, where you have to figure out some way of handling cycles within them? It's a little tricky, right? It may or may not be easy to do, and you may end up doing it. Here's some of the ways that you can deal with it. One, weak pointer is a reference, but you can use it to validate if it's still a valid reference or not. There's something called enable shared from this, which for certain types of cycles is a very easy way to deal with it. In other words, you can say the ownership is the actual object itself. And that can be then shared for a particular period of time or until it gets to a certain maturity or its lifetime. That can solve certain types of cycles. You can design them out. Most gaming engines have tremendous cycles. How do they deal with it? Some design it out. Some use different techniques in indirection. Hiding objects and references to textures behind a lookup table, common technique. Certain large gaming engines do this. Others, they use other ways to get rid of the cycle. RCU, read, copy, update, quiescent state-based reclamation are other techniques. RCU, used in a Linux kernel. A lot of the reasons why you come up with cycles is because of the relationships and dependencies that are there. Some of those are not truly your responsibility. Deferred destruction is a way of handling that. It is garbage collection. It is a form of garbage collection. So you can deal with cycles. Now, the last one there, deferred and unordered destruction, is Herb Sutter's sort of experiment of providing a GC-like ability within the runtime. And it is being looked at for things like C++ 17 and greater. So there are many different ways to deal with cycles. This is not unique to modern C++. So cycles aside, having just those 3 types of sort of ownership models makes coupling explicit. Because that's the only ways that you have to look at other objects that are coupled. The scoping becomes extremely explicit because now it is the lifetime of that shared pointer, that unique pointer, and all the others that are pointing to it. You have explicit dependencies as well that start coming out. The reason that it sort of becomes extremely explicit is you have to think about using them. It's not simply something that just kind of gets generated for you. What's the difference between a unique pointer and shared pointer? Unique ownership versus shared. When do I use one versus the other? Why would I use a weak pointer to it and I have to validate it every time I have it used and then inflate it to a shared pointer? It makes all these relationships a lot more concrete and a lot more explicit. And sort of as the journey of this, because originally you start this out and you're like, oh, okay. You start thinking about things that you didn't think about before. The ownership and lifetime is something that you might have thought of before, but now you can't hide from it. So if you come from other languages, this seems like a burden because you might have garbage collection to sort of handle that for you or to hide it. But hiding complexity is not really dealing with complexity. It's basically just putting it off until something else happens. In certain cases, that's the right way to handle it, but not in everyone. RAII has that other part of it, which is when that resource is given up, it is given up as quickly as possible. It doesn't just linger around until someone needs it. There are actually, within Aeron, instances where the Java side cannot rely on GC to just decide that it wants to kick in. So we've had to go in with reflection, grab a function, and then explicitly call it because we can't wait for that to be done by the garbage collector. Really, when you think about coupling, scope, and dependency, and you look at the structure of any project, it speaks to the quality of it. If you see a lot of, just shared pointer used everywhere, and things that are, definitely circular, but they're using shared pointer between them, that's probably a big red flag. That speaks to the quality of it. But you got to build quality in. And where does quality start? Quality starts with requirements. Originally, my career started by being a researcher for NASA on software quality. And I can tell you that any problem that you find in requirements, the sooner you address it, the less work you have later on. So you build quality in at the start. So looking at object relationships and entity relationships and looking at explicitly making coupling in the scope and the dependencies right there in front of you has a tremendous benefit to you. In fact, it has such a benefit that we actually have things now that their main advantage is the fact that they enforce decoupling and isolation. What does this? It's the best thing about microservices we have. That enforced decoupling of different components. And that asynchronous binary boundary between those components is actually one of the best things about microservices. It forces us as designers, as architects, to think about those systems and we can't make them tightly coupled in the traditional way. Can we still couple them? Yes, we can still make them very dependent, but it's now much more explicit. The same kind of thing. If you think about it, step back about this for a moment, what is more important? What a language provides or what a language takes away? What have we seen with things like Go and Rust? Have they added a lot of new things? Or have they restricted what we can do? In a lot of cases, they have added nice features, things that we want to them. But they've also, Rust especially is an example where it has said, no, you can't share between threads. No, you can't do that. It's provided isolation. So what languages take away sometimes can be just as important or maybe even more important than what they provide. So here's some, when thinking about the sort of scope and dependency and coupling, the idea that you're restricted to just those three types of ownership models and how they interact, deal with it up front. It pays off massively later. And basically, it looks sort of like this. Initially, it hurts. And trying to wrap your head around exactly how this should be. But what happens in the end is you get better at it. With Aeron, which was the first project, it was a little twisty. It was not quite what we wanted. It wasn't right. And then we kind of gave in and we thought, oh, okay, this looks better. With Reactive Socket, it was do an iteration. That doesn't look right. Do an iteration. That doesn't really look right. Do a little iteration. Well, that's better, but that's not, good. And after a few more iterations, it's gotten better. Is it where we would want it? No. But it's much better than it was. So it's that iterative, making it better each time. And you notice different relations that you didn't previously. So smart pointers are the thing that is, for a lot of projects, something that is initially struggled with. The sooner you give in and you say, this is what I have to deal with, and this is sort of how I have to think about it, and you look at it explicitly, things get a little bit better. Stack allocation's been around forever, and it is a part of our AII. And sort of, whenever I talk to people who, in the Java community, and I do a lot of Java. Usually when I point out the stack allocation is great, why doesn't Java let us control the stack explicitly? And the answer usually starts like this. It's not needed because. Have escape analysis. Have value types. Input whatever kind of other thing here. And the argument usually goes, well, escape analysis, you know what the answer to escape analysis is almost every time? It escaped. It'd be the worst prison in the world. Because everything escapes analysis. The default answer is it escapes. So you can't really get what you would want from it. Value types, that's one small use of stack allocation, and it's not even a really good use of stack allocation. Value types have other advantages. But trying to say that you don't need stack allocation because you have value types is kind of like this. And then you keep going, and I feel a little bit more like that. You know, it's like, and really what this boils down to is stack allocation is a mechanism. It's not a set of features, right? You're not going to say that you don't need stack allocation because you have, you know, garbage collection. That is one feature, but it's not the mechanism. The mechanism is important. Here's a use of stack allocation that has nothing to do with any of the things that were mentioned previously. It's basically making a function object, storing the state of it on the stack, and then passing it into another function. This can be very, very low cost, deferred or conditional execution based on that function. You can do this before you could do, you could do this back in 95, 96. And it's a nice, simple thing to do. It also is very efficient. Can you replicate this in Java? Not if it's capturing, which it's going to capture. If I'm calling this 100 million times, it's going to allocate. It's going to then run the GC. So you can't quite get it. It sort of loses its main reason to exist. Move construction and assignment. So this was the big money feature of C++ 11. You would think everything now uses move construction when it's appropriate. And here's the best advice. Move construction and assignment is much more than you think. Moving an object, transferring ownership, works in a lot of situations. So yes, using it when it is appropriate is great. But sometimes it's even better to copy. The idea that you transfer ownership does require that there is a little bit of synchronization. And when you're just doing something like moving it from one thread to another, a move is not the right one. You would rather have something which is copied. And it's, do you actually even have to transfer ownership? That's another question. Here's another way that things are really kind of interesting is optimization interactions. SSO is short string optimization. It turns out that strings that are short have a lot of optimizations around them. In fact, 24 bytes of a string is dedicated for just short strings, so that you don't have to allocate anymore. You just allocate the string, boom, you do something with it. As long as it's less than 24 characters, you're great. Why in the world they picked 24? I do not know. But 24 turns out to be a great number. How do you move a statically allocated 24 bytes of memory? The answer is you don't. You copy it. So that move looks exactly like a copy. So how do you get the optimizations that you would want from the move? You don't. And there are other optimizations, like copy elision, where it looks like a copy, but the actual optimizers looked at it and said, nope, don't need a copy. And so you'd lose out on some of that because move has not been optimized as much as copy has. And the other question is, when you have to do it, why? Why are you transferring ownership? A lot of times, you may not actually need to transfer the ownership. The next one is atomics. And if any of you have seen the movie Dune, this may make sense. If you haven't, it's probably Patrick Stewart in some sort of uniform. Let's go back to Aeron for a moment. So Aeron, with the C++ pieces, sort of lives around the clients. But all those different interactions, like with the log buffer, the ring buffer, and the broadcast buffers, those are all shared memory atomic operations which have ordering requirements. What Aeron does at its heart is replicating a persistent log of messages. It has a file, and it has ordered and atomic operations which are done in memory on those items, the different terms and the log metadata. I don't expect you to realize what a term is or what the log metadata is. Just realize that within this file, which is mapped into memory, there are ordered and atomic operations which are done all over it. But that's not the only thing. The concept of a position within that log is a unique identification of the byte. Publishers, senders, subscribers, and receivers all keep position counters. These are key to flow control and monitoring. They have, statistics and position counters accessible in shared memory, which means that accessing them, updating them, reading them, has atomic and ordered operations associated with them. So if you're going to have something like a media driver or different applications interacting with one another, they have to have the same sort of ordering semantics and everything else. These are challenges. Here's the challenges in using stud atomic. Size and layout. And the memory model, C++11 to Java. These are two very big challenges. The first is size matters. Size matters an awful lot. If your integer has padded zeros in the front of it, and on one side and the other side doesn't understand that there's padding there, is that a problem? Yep, it's not the same size. What is your integer? 32-bit signed, 32-bit unsigned? It turns out that atomics within C++11 were not designed for arbitrary memory access. They were actually designed for members of a class that could control their own layout and everything else. And they don't have to be the same size as the type. So your int on some systems is 32, on others might be 64. So it's only really concerned with the order of operations. It's not concerned with the size. So interoperability with the Java memory model is hard from a size performance, but it's also different from a memory order. Memory order is fit for purpose. In other words, the memory order that you use within C++11 infers a particular type of semantic. That semantic is just ever so slightly different from Java. Just enough that there is less control that you can enforce. You can make it kind of work if the size would work, but memory order is sort of a little bit tricky to do when you're interacting with other things which have just slightly different semantics. So what did we do? Well, luckily we had a contributor that took the initiative, went through the JVM code, looked at the actual instructions which are emitted and how they are basically then kept from being reordered, and basically allowed us to use that as a set of atomic operations that are sort of compatible. So it looks like the same code, the same assembly. So it has the same, additionally, it has also the same compiler restrictions of moving certain code in certain directions as well. And then I took that and then sort of went with it and refined it and still refining it. There's one type that's still not right. Volatile. Oh, it's put volatile. Still not right. That's a challenge. Looking at it up front, we kind of identified that this was a potential area and how to deal with it. We went through various different iterations to make it work. So wrapping up, sort of covered different things. The things that you would normally think of that were on that list that weren't problems, things like thread functions, not problems at all. Tool chains, not problems at all. Stack allocation wasn't really a problem. It was just something which was leveraged. It really isn't that different. But it is something which does change, sort of the way that you think about APIs and object ownership, because it does have an effect. But wrapping up, think of languages, always think of them as tools. Think about fit for purpose. And I'm not here to sort of say that you should be using C++. You know what you need to do. You should realize if C++ is the right tool for it or not, and figure out, if that is going to be, sort of go into that with your eyes open. Does it work for what you're trying to do? Is it fit for that purpose? And add that to your toolbox. You should always be thinking about a language as something which is a tool. If it has, it just so happens that languages are tools that can be used in a lot of different ways. So think of it that way. And the other thing is, don't think too much about a language and categorize it as just one thing. Because there's a lot of systems out there that, basically are been put in some awful languages, and there's a lot of other beautiful languages that simply just haven't been exercised within really complicated domains. So don't really think about the language so much as, does it meet what you're trying to do? And do this too. So Aeron is an example of this. taking on a new idea when you've done it several times. Both Martin and I have done messaging systems several times. So doing it in a different way. We didn't know if it was going to succeed or not. Luckily it has, but we went into it thinking this would be interesting. Reactive socket is, this would be interesting. If this works, then it provides something which is sorely needed to simplify logic composition and do that across languages. That's pretty cool. So and then say, okay, well, we'll do this in C++ too. Okay, all right. What does that mean? So don't be afraid to try new things and look at things from that perspective. Here's a couple links where you can look at both of these. I would say that in terms of maturity, Aeron's C++ side is much more mature than the reactive socket side. Reactive socket side is newer by quite a while, probably a year or more, and it is still undergoing some massive changes. But freely would love to have feedback and things like that. But it's not too far from being actually in production. And with that, do you have any questions?